Welcome back, students. In this video, we are going to go through Chapter 5. Chapter 5, Section 1 is Probability Distributions. So this section introduces the concept of a random variable and the concept of probability distributions. So we are going to be using a lot of what we did, I believe, in Chapter 2 when we talked about histograms. And now we're doing a probability histogram. And it is a graph that visually depicts how probabilities are distributed. So we will show how to find the important parameters such as mean, standard deviation, variances for a probability distribution. And we will determine we will describe how to determine whether outcomes are significant. So the requirements for probability distribution. They must satisfy the three requirements. There is a numerical random variable x, not categorical, meaning that everything must be quantity, not qualitative, and the number of values are associated with corresponding probabilities. The summation of the probabilities must equal 1, meaning that you can't have the sum of all the probabilities being more than 1 or less than 1. They must be exactly 1, minus rounding errors, they feel the need to say. And then each of the individual probabilities must have a probability between 0 and 1. You can't have a probability greater than 1, and you can't have a negative probability. So, without further ado, let's go straight to an example. I always find that when I was a student, I learned really best when we talked about an example. You can give me all the rules and words in the world, but until I see you practice it on an example, I don't fully understand it. So let's consider tossing 2 coins with the following random variable. And then we say x is the number of heads that occur when 2 coins are tossed. So the above x is a random variable because its numerical values depend on chance. So what are the possible outcomes that we get when we flip 2 coins? Well, coin 1 could be heads or tails, and then coin 2 could be heads or tails. So the possible outcomes are as follows: heads, 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 tails, tails, heads, and tails, tails. There are 4 possible outcomes. So now we're interested in the number of heads that occur when 2 coins are tossed. Well, we can have either 2 heads, 1 heads, 1 heads, or 0 heads. And how many of each of those occur? Well, there's only one scenario where 2 heads occur. There's only one scenario where 0 heads occur. And then there's 2 in which 1 heads occurs. So since we're dealing with 4 total probabilities, 1 out of 4 is 25%, 2 out of 4 is 50%, and 1 out of 4 is another 25%. So here is your probability distribution. But we want to depict that on a histogram. So let's first check our requirements, and we'll find that the requirements are met. The variable x is numerical, the sum of all probabilities equals 1, and each individual probability is somewhere between 0 and 1. Okay? So the random variable x in the table is a discrete random variable because it has 3 possible values, and 3 is a finite number. So it satisfies that requirement as well. So now we're going to put that on a probability distribution histogram. So it's similar to relative frequency histogram, but right now the vertical scale shows the probabilities, not just the relative frequencies. So the vertical scale over here is the probabilities, and it's based on actual sample results. So the probability histogram for a number of heads and 2 coins are tossed, you can see it can be either 0, 1, or 2, and this is kind of getting that general normal curve shape as well. So let's look at another example. Hiring managers were asked to identify the biggest mistake that job applicants make during an interview, and the table below is based on their responses. Does the table below describe a probability distribution? Well, we got 0.5 for inappropriate attire, 44% were late, 33% lacked eye contact, 30% were looking at their phone during the interview, and the total is 1.57 if you add all those up. So does this satisfy the requirements? So the table violates the first requirement because x is not a numerical random variable. The values of x are categorical data, not numbers. Remember, it needs to be quantitative, not qualitative in nature. The table also violates a second requirement because the sum of the probabilities is 1.57, but it needs to be 1 exactly. So because the three requirements are not satisfied, we conclude the table does not describe a probability distribution. Okay, so the parameters for a probability distribution are as follows. We have the mean is given by this equation. Remember, this is a sigma, which is the summation. Variance is this equation, standard deviation here. And I'm just showing you these for FYI. You will need to give me these answers, but I do not want you to use the formulas. They are there for your information. I want you to use technology instead. So I am showing you how to do them. I am giving you, here are the step-by-step instructions, and here's a YouTube video which will walk you right through getting a probability distribution parameters using the TI-84, and then again using StatCrunch. Very simple instructions. Just watch that YouTube video. It's very quick, and then you'll be able to get the parameters as well. Okay, the next topic of this section is going to be expected value. And this is actually one of my personal favorite sections, or really mini sections of a section. I think this is fun because I enjoy going to the casino. And this is really where casinos crunch their numbers when they put out games. So expected value. The mean is sometimes called the expected value. So the mean over here, this is often called the expected value. And the expected value of a random variable x is equal to the mean mu. And we can find the expected value by computing the summation, just as we do for finding the value of mu as well. So let's look at an example. So be a better, kind of a funny play on words. You have $5 to place on a bet in the casino in Las Vegas, and you have narrowed your choice down to one of two bets. You can either bet on number 7 in roulette, or you can bet on the pass line in the dice game of craps. Craps is probably my favorite game, but that's not really relevant to the class. Which of the preceding two bets is better in the sense of producing higher expected values? And what we mean by expected values is, as you play a game infinite number of times, what can you expect to be your mean result? And your mean result's going to be different than what you'll actually get from any individual result. What we're saying is, as time goes on, if you average out all of your winnings or your losings, you're going to get this expected value. And it's always going to be a negative value, because if it was positive, the casinos would lose money. So don't be shocked if your expected value comes out to be negative. Okay, so let's look at A. A, again, was looking at the roulette scenario. So if you bet $5 on the number 7 roulette, the probability of losing that $5 is going to be 37 over 38. Remember, there are 38 total spaces for that ball to land on. 18 red, 18 black for 36, and then there are 2 greens for 38 total. So there's a 1 in 38 chance of getting it correct. So there's a 37 out of 38 chance that you'll lose $5, and then there's a 1 in 38 chance that you will have a net gain of $175, which is the 35 to 1 odds that we talked about in the previous section. So the prize that you would get if you get it on 7 and guess 7 is $180, including your $5 bet. So the net gain is $175. So find your expected value if you bet $5 on the number 7 in roulette. Okay, so now we're taking into consideration the odds of losing and the odds of winning to determine what your average or your mean outcome is going to be if you play this infinite amount of times. So roulette, the probabilities and payouts for betting $5 on the number 7 are summarized in the table below. Okay, so we have two events, either losing or winning. And when we win, we talk about net gain. We don't talk about the $5 that you bet originally. So if you lose, the net outcome is going to be negative $5. If you win, the outcome is going to be you win $175. The probability of losing is 37 out of 38. The probability of winning is 1 out of 38. So this column right here is summarized by doing x multiplied by the probability, gives me negative 4.86. The event of winning gives me $175. The probability of winning is only 1 in 38. So multiply 175 by 1 over 38 gives me this expected value right here for the event of winning. Once you add them up, this value right here is going to be your expected value or your mean value. So if you played roulette, I don't know, 1,000,000 times, the average or the mean of what you got per round is going to be negative 26 cents. So you are expected to lose an average of 26 cents each time you play roulette. So in other words, if I played 100 times, I might lose $26. So $26 divided by 100 times means that I lose on average 26 cents per round. Okay, so that's be a better. So now let's look at, we just talked about roulette. Now let's look at craps. If you bet $5 on the pass line in craps, the probability of losing $5 is 251 over 495. And the probability of making a net gain of $5 is 244 over 495. If you guys have ever played craps before, you would know that if you bet on the pass line, you are betting with the players. And if you bet on the don't pass line, you're actually betting with the house. And everyone hates you because you're playing with the enemy. But we're betting on the pass line, so let's continue. So you bet $5. There's a 251 over 495 chance of losing and a 244 over 495 chance of winning that $5. So you can see that the odds of losing are slightly higher than 50%. If this number was equal, they'd be exactly even, but this is a little higher, so the odds of losing are a little bit greater, which of course makes sense because the casino is not there to help you make money, they're there to win money. So we want to know, what is your expected value if you bet $5 on the pass line? And then which of the preceding two bets is better in the sense of producing a higher expected value? So same thing right here. There are two events. We either lose or we win. If we lose $5. If we win $5. The probability of losing is 251 over 495. Probability of winning is 244 over 495. So the x times the probability is going to be -5 times this probability gives us negative $2.53. And if you win $5. Multiplied by the odds of winning gives us this right here. And this should be positive. That's not a negative value. Let me see if I can change that right now. Nope, it's a picture. For the record, that mistake was not by me. That was by Pearson. So sorry about that. One more time. This should be a positive value. Positive times a positive is not a negative. I don't know how they made that mistake. But you add those two values together. Negative $2.53 plus $2.46 gives us negative 7 cents. So the expected amount to lose on average is 7 cents per round of craps. So the $5 bet in roulette results in an expected value of negative 26 cents, and the $5 bet in craps results in an expected value of negative 7 cents. And the interpretation is saying, because you are better off losing 7 cents instead of 26 cents, craps is better in the long run, even though roulette provides a better opportunity for a larger payout. If you're trying to actually win a sizable amount of money, you're not going to get it winning $5 a time. You're better off with roulette. But we're not looking at it from that aspect. We're just saying which one has the better expected value. And that would be craps. Okay, that concludes this chapter and section. Any questions, let me know.